Greetings and welcome to Mr. Van Loo's poorly monetized low-budget science channel. Do not click like, do not subscribe. Okay, today we're going to be talking about topic 2.4 in IB Physics, and this topic is about momentum and impulse. Your learning objectives, and I recommend listening to this at double time. Your learning objectives are to apply conservation of momentum in simple isolated systems, including, but not limited to, collisions, explosions, or water jets. Second, use Newton's second law quantitatively and qualitatively in cases where mass is not constant. This actually doesn't come up that often, but anyway. Sketch and interpret force-time graphs. We'll take a look at a couple examples of those. And determine impulse in various contexts, including, but not limited to, car safety and sports. Qualitatively and quantitatively compare situations involving elastic collisions, inelastic collisions, and explosions. And if you're wondering, qualitative, the root is quality, so you're looking at characteristics. Quantitative, the root is quantity, so you're looking at calculations and quantities and such. Okay, so let's start with linear momentum. It is given in your data booklet, conveniently, and it's given as momentum is p, and it's equal to mass times velocity. Okay, so we use a little p there for momentum, and you guys know m and v, they're mass and velocity, or I should say you people. Because I may have female watchers or listeners, and I want to be inclusive. So note that since velocity is a vector, it has direction, and momentum then must also be a vector. So you could put a little arrow up here to indicate that it's a vector, and then a little arrow above the v would also tell you that velocity is a vector. Mass is not. Mass is a scalar. Okay, next up. You might be asking yourself, if we have mass and velocity, why would we not just calculate kinetic energy? We've already learned about this, and it seems really convenient. And this is the kind of smarty pants question that could potentially throw your teachers. However, I have an answer. First, momentum is convenient when doing calculations involving collisions, and we'll look at some examples later. Second, according to Newton's second law, and we'll derive this in a second, the rate of change in momentum over time is going to give you the net force of a system. So that's really, really useful. Finally, momentum is conserved, but kinetic energy is sometimes not. And yeah, we'll see that in a little more detail as well. So Newton's second law in terms of momentum is given by this equation, where net force is equal to a change in momentum divided by a change in time. Okay, so we can quickly convert this to the form of Newton's law that you're familiar with, which is where force is equal to mass times acceleration. And it's going to look a little bit like this. So we have our initial equation, and we know that a change in momentum will be equal to the final momentum minus the initial momentum. And this is typically the case wherever you have a change in something. There are some examples in topic 3 where we reverse this scenario, but final thing minus initial thing will give you the change in the thing. Okay, so we're going to assume that mass is constant here, so we can substitute mass times final velocity minus mass times initial velocity, and this is all divided by change in time. Okay, so we factor out mass, and you may now recognize that this is looking a lot like acceleration, and it is. So there's your derivation. Okay, so what we recognize here from this equation pretty much right away is that net force is inversely proportional to time. Directly proportional to momentum, but inversely proportional to time. And what that means is that if we increase the amount of time in our system, then we're going to decrease the net force. Okay, so this is why in cars your seatbelts are stretchy, because by stretching, it increases this amount of time, after a collision occurs, and that means that your body is going to experience less force, and that could potentially save your life by preventing your insides from turning into jelly. Okay, crumple zones are similar to the seat belts in that they increase the amount of time and spread out the force, decrease the amount of force, which again may save your life. Okay, now we can take this equation and shuffle things around a little bit so that our change in momentum is equal to force times a change in time. And impulse then is defined as a change in momentum, delta P. So then this is in your data booklet as impulse is equal to force times a change in time, which is then equal to a change in momentum. Okay, so impulse, change in momentum, done. Okay, so here we have impulse as shown on a force and time graph. And what you'll note here is that we have a curve, and sometimes curves like this can involve some pretty nasty math. And to calculate the area underneath this curve, which is what we would need for momentum, we'd have to use calculus, okay? So we don't do calculus in IB physics. So what we would do instead of integrating a kind of unfortunate equation is we could just use small rectangles of equal width, okay, to approximate this value under here. And yeah, again, more exact value is going to require calculus. This is a little bit nicer because we have a constant force being applied here, and we could just calculate the amount of constant force using a rectangle, looking at the area underneath this line. Okay, so the area of the rectangle will give us our impulse then. Okay, here we have force varying linearly with time. And in this case, we would want to use a couple of triangles to calculate our net impulse. Okay, so we have the impulse given by triangle A and the impulse given by triangle B. And to calculate net impulse, we would just subtract from the area of this triangle, the area of this triangle, okay? Pretty straightforward. We could then, you know, in some conditions, under some circumstances, we could have then negative net impulse, and that would be fine. Not the end of the world. All right, next we're going to take a look at conservation of momentum, where if we have a closed system, the net force acting on the system is 0, and then the momentum of that system must therefore be constant, okay? And this is going to look a lot like Newton's first law, okay? In this case, our momentum is conserved. And for IB physics, you should assume that the momentum is conserved because for collisions or explosions, that will generally be the case. Okay, as we mentioned earlier, kinetic energy is not always conserved. And so then in collisions, our kinetic energy could be lost to friction or sound or the squishing or deformation, distortion of the object, etc. Okay, so there are a lot of ways that we can actually lose some of the energy in our collision. Okay, so we have two types of collisions. First one is called an elastic collision. And in an elastic collision, our objects are not going to stick together. And in this case, where objects are not sticking together, we will consider kinetic energy to be conserved. An inelastic collision would be sticky, and in this case, kinetic energy is not conserved. Okay, so for IB physics, we're going to assume that our collisions are 100% one or the other, but in reality, this is not true. So for example, you could think of a billiard ball colliding with another billiard ball, and this would be a mostly elastic collision. But if you've ever played billiards or pool, you will know that the balls click when they hit each other, and sometimes that can be quite loud, okay? And we're going to lose some kinetic energy in that example, okay? But for IB physics, we're just going to assume that it's 100% elastic or inelastic done. Okay, so we can derive this relationship between kinetic energy and momentum using a little algebra. And here it is. I'm not going to go through this whole thing. You can look at it carefully. There's a little substitution involved here. Or rather, what I've done is multiply the numerator and denominator by mass, and that produces m squared on the numerator and m in the denominator. And this, of course, is momentum squared divided by 2m. So kinetic energy is equal to momentum squared divided by 2m, and that's in your data booklet. So this is a handy shortcut. You will see a number of circumstances where it can be useful. Okay, so next, conservation of momentum can be expressed as initial momentum being equal to final momentum. And this is typically the case wherever you have, excuse me, conservation of a thing. Your initial conditions will equal your final conditions, and therefore you know that you have a conservation law. Okay, so as we've discussed, in elastic collisions, our objects don't stick together. Our masses are typically going to remain constant, so a change of momentum will usually be due to a change in velocity. But you can't imagine some scenarios where the mass would not remain constant. I guess an example of that would be like, let's say you have a bucket on a cart, and the bucket is filling up with water due to rainfall. So that's going to increase the mass. And if your momentum is conserved, that's going to change your velocity. So these usuallys are pretty important caveats. Okay, so we're going to talk about elastic collisions here for a second. Elastic collisions occur when our objects bounce off of each other. Here I have two objects headed straight for each other. And our momentum here can be described by this equation, where we have the momentum of object 1 right here and the momentum of object 2 right here being equal to the final momentum of object 1 and the final momentum of object 2. And this little prime mark here is just a way that we can indicate that this value here is going to be different than this value here, okay? So, defining our variables, p sub 1 is the momentum of the object before the collision, p sub 2, same thing for the second object, and p sub 1 prime is the momentum of object 1 after the collision, p sub 2 prime, you can read, so you get the idea here, okay? So, this just helps us not have 500 variables for our equations. All right, so we know that momentum is equal to mass times velocity, and so we can do a little bit of substitution here, and that's going to give us this new equation where we have the momentum of object 1 plus the momentum of object 2 equaling, so this is pre-collision and this is post-collision, so the momentum of object 1 and object 2 post-collision over here. Okay, and I'm just gonna quickly show these, and you can pause the video if you want to take a closer look at them if you need to. Okay, so for inelastic collisions, our equation is actually simplified a little bit because you'll recall that inelastic collisions are sticky, meaning our objects are going to stick together. So in this case, these two spheres would be like clay or something really, really sticky. So so our objects are now stuck together following the collision, and this is going to produce a single mass with a single velocity, and that makes our equation a little bit nicer. We don't have the prime marks anymore. Life is good. Life is good. And defining all of our variables, There they are. So we've got our masses, we have our initial velocities, and then we have our final velocity here, v. Okay. All right, what else do we have? So here's how explosions look in reality. I believe this is a rocket exploding. And you can see these little bits of stuff flying all over the place. And if we really wanted to do the math, we would have to account for the velocities, the initial velocities of all these particles, and it would be a real pain. But in IB physics, we don't have to do that because this is what our explosions look like in IB physics. Little disappointing. Not quite as cool. So the main difference here, though, is 3 dimensions versus 1 dimension. So this is a 1-dimensional explosion, and this is a 3-dimensional explosion. So thank you, IB. They've made your lives much easier. So in both cases, momentum is going to be conserved. And again, initial momentum is equal to final momentum. So since the initial momentum prior to the explosion is 0, we can state in this case that the momentum of object 1 will be equal to the momentum of object 2. One of our velocities is going to be negative. Okay. The cart moving to the left should have a negative velocity according to the conventions given by Descartes and his Cartesian coordinate system. Okay, really though, you could have either velocity being negative as long as you know what you're doing. I recommend sticking with Cartesian coordinates. Okay, so the physics involved here are a consequence of Newton's third law. We have equal and opposite reactions. So our carts only show one possible one-dimensional application, but other examples could be skateboarders pushing away from each other. This is kind of a common thing in IB physics. We'll put wheels on people's feet and then have them push off of things. Another one would be astronauts pushing off of each other in a space station, or possibly another object in 0G. And that is going to look a lot like an explosion. And there will be other examples in IB physics. There are more than we can possibly cover here. So, key point though, you will not need to deal with explosions in 2 or 3 dimensions. It's not that it's much more difficult. It's just a little tedious. You'd have to break down the velocities into vector components, horizontal and vertical, and also along a 3rd dimension like a z-axis. So you'd have x, y, and z, and yeah, pretty tedious ultimately. Okay, here we have water jets, and these require pushing water out of one end of an object, such as a water rocket, which you can see here. And these are tons and tons of fun, so you should get one and play around with it. Okay, the principles here are similar to an explosion with an important exception, and that is that the mass of the object will change over time. And what that should tell you is that quantitative analysis is going to require calculus, which we don't do in IB physics. Okay, this would involve, I believe, differential equations. So I don't recommend these for IAs because data collection is tricky at best and really time consuming. And also the fact that you'd have to do calculus for quantitative analysis means that students often do water rockets. I've seen IAs like this before, and the results have been generally not fantastic because it's just too much. It's a little too much for a lot of students. Okay, your sources here, as usual, Sokos, Physics for IB Diploma, very good textbook. There's the image. Desmos normal distribution was my starting point for some stuff. water rocket image, explosion GIF. There's actually, I did not use this in the presentation, but if you want to check it out, it's pretty cool. I did use Algodoo for the two-dimensional carts, and Algodoo is a lot of fun, and it's free. You can download it for free, so you should do that. Okay, have a good day, everybody, and remember, do not click like, do not subscribe. If you do, I'll forgive you, though. Okay, bye.